Hello students, good morning. You are welcome in the lecture number 3 of a chapter of Ionic Equilibrium. In the last lecture, we have started with theories of acids and bases. In all, 3 theories we have completed, that is classical theory, then Arrhenius theory, and finally Lorry and Bronsted theory. According to classical theory, only the properties of substance are used in order to define them. Acids are explained on the basis of their properties, as well as bases are also explained on the basis of their properties. But a structure of acid or structure of base is not explained at all. Therefore, first of all, it is the Arrhenius theory we have studied. We have explained in short the structure of acid and base. According to Arrhenius theory, we have seen that acid is a substance which gives H plus ions in aqueous medium. Base is a substance which gives OH minus ions in the aqueous medium, that is water. The substances, whenever added to water giving H plus ions, are known as acids, and the substances which whenever added to water giving hydroxide ions, that is OH minus ions, are known as bases. But we have seen there are certain drawbacks to that theory. The important drawback is that only medium is important rather than a substance. HCl is acidic whenever added to water, but if HCl is added to some other solvent, it may not be acidic. Medium is important rather than a substance. There are some drawbacks we have studied, like existence of free H plus ions is not explained. The substances which are neither containing H plus nor OH minus also show acidic or basic behavior. They are not explained. Therefore, that theory is replaced by Lorry and Bronsted theory, where irrespective of medium, acids and bases are defined. Acids are defined as a substances which are capable of donating the proton. Proton donors are acids, and bases are the substances which are capable of accepting the protons. Proton donor is acid and proton acceptor is base. Irrespective of medium, acids and bases are defined according to Lorry and Bronsted theory. And in that theory we have studied that whenever acid is added to the base, acid donates proton, base accepts proton, and transfer of proton take place from acid to the base. Transfer of proton take place from acid to the base, and conjugate acid-base pairs are obtained, where conjugate acid is having one proton greater, one proton more as compared with its conjugate base, and the conjugate base has one proton less as compared with its conjugate acid. There we have seen the amphoteric nature of water. Water whenever added to acid shows basic behavior. Same water whenever added to the base shows acidic behavior. Both acidic as well as basic properties are present in the water. Therefore, it is known as amphoteric substance. Till some of the substances are not explained as an acid or base according to Lorry and Bronsted theory. Therefore, next theory is developed, that is the Lewis theory, Lewis concept of acid and base. Now let us see Lewis concept of acid and base. According to Lewis theory, acids and bases are defined. Acid is defined as a substance which is capable of accepting lone pair of electrons. The substances which are capable of accepting the lone pair of electrons is known as acid. And on the other hand, base is defined as a substance which is capable of donor of lone pair of electrons. Donor, this is donor and this is the acceptor. The substance which is capable of donating the lone pair of electron is known as base. So acids and bases are defined on the basis of whether it is capable of accepting lone pair of electron or donating the lone pair of electron. Now here these substances like those which are neither containing H plus nor OH minus ions are also explained as an acid or base according to Lewis theory, Lewis concept. Now let us see the example. Suppose we have the substance like BF3 boron trifluoride. It is acidic according to Lewis theory. It is acid according to Lewis theory. Is it containing H plus ion? No. Is it containing OH minus ion? No. Still it is acidic. All the properties of acid are present in boron trifluoride. So why it is acidic can be explained on the basis of Lewis concept. It is acidic. See how this is acidic now. We know boron has atomic number 5, electronic configuration 1s2, 2s2, 2p1. 1s2, 2s2, 2p1. So how many electrons are there in the outermost valence shell? There are 3 electrons present. For the boron, there are 3 unpaired electrons present. For fluorine atom, atomic number 9, electronic configuration 1s2, 2s2, 2p5. How many unpaired electrons are there? Total electrons 7. Out of that, 1 electron is unpaired, which can be shared for bonding. Now, the structure of BF3 is like this. BF3 boron trifluoride. During the formation of BF3, each boron or one boron shares 3 electrons, 1, 2 and 3. So 1 electron of boron, 1 electron of boron and 1 electron of boron. 3 electrons of boron are shared with 3 unpaired electrons of 3 fluorine atoms. Fluorine has totally 7 electrons. So 2, 2 and 2. 6. And 7 is here. Similarly for this boron, 2, 2 and 2. One more unpaired electron is here. For this also 2, 2 and 2. One more unpaired electron is here. Now there is a sharing of electron between fluorine and boron. Here fluorine boron, fluorine boron. How many bonded pairs of electrons are there? 3 bonded pairs. There are 3 bonded pairs of electrons present around the boron. How many electrons are there around fluorine? 8. Now it is 8. 2 plus 2 plus 2 plus 2. So 8 electrons around the fluorine. Around this fluorine also 8 electrons. Around this fluorine 8 electrons. But how many electrons are present around the boron atom? Only 6. There are 6 electrons present around the boron. 2 plus 2 plus 2. In order to complete the octet, how many electrons are required? We know it requires 8 electrons. It will require the 8 electrons, but there are only 6 electrons present. Therefore, boron is capable of accepting one more lone pair of electron. 2 electrons can be accepted by the boron in order to complete its octet. Therefore, it is nothing but the lone pair of electron acceptor, and it is known as acid. This is the acid. Now see the case of ammonia, NH3. You got it? How BF3 is capable of accepting the lone pair of electron? Because boron has 6 electrons around itself. In order to complete the octet, it requires totally 8 electrons. Therefore, it is a lone pair of electron acceptor, and this is acting as an acid. On the other hand, if we see the case of ammonia, NH3, see here the structure of ammonia. In ammonia, nitrogen is central atom, atomic number 7, electronic configuration 1s2, 2s2, 2p3. So how many electrons are there around the nitrogen? Total 7 means 2 plus 2 plus 3. There are 5 electrons in the second cell. There are 5 electrons. H, hydrogen, atomic number 1, electronic configuration 1s1. So whenever NH3 is obtained, whenever NH3 is formed like this, 3 unpaired electrons of nitrogen, 3 unpaired electrons, only these 3 unpaired electrons of nitrogen forms a bonding with unpaired electron of hydrogen. One hydrogen has how many unpaired electrons? Only one. So that one unpaired electron of hydrogen forms a bonding with unpaired electron of nitrogen. Unpaired electron of nitrogen here also. So how many electrons are there at present? It is 6. It is 6 around nitrogen. But still there are these 2 more electrons. 2 more electrons are present on the head of nitrogen. Now how many total electrons are there around the nitrogen? 8. Octet of nitrogen is completed. But this nitrogen is containing a lone pair of electron. Lone pair of electron, free pair of electron for donation. So whenever it is added to other substance, this is capable of donating the lone pair of electron. And any substance which is capable of donating lone pair of electron is known as base. Therefore, NH3 is base. It is lone pair of electron donor, so it is base. This is lone pair of electron acceptor, so it is acid. Whenever reaction between acid and base take place, acid accepts a lone pair of electron, base donates lone pair of electron, and there is a formation of a coordinate bond take place. Coordinate complex is obtained. See here, BF3, boron trichloride. Here boron has incomplete octet, and boron is capable of accepting the lone pair of electron. This is added to NH3. Here nitrogen has one lone pair of electron, and it is capable of donating that lone pair of electron. This is acid, this is base, according to Lewis definition, Lewis concept. And now the reaction takes place. Boron accepts lone pair of electron to complete the octet. Nitrogen donates lone pair of electron, since there is no effect on the octet, and the compound octet, product octet is like this: BF3 NH3. This is a bond formed between boron and nitrogen. Now can you tell me, during the formation of bond between boron and nitrogen, is it equal sharing or unequal sharing? What is it? Unequal sharing. Both two electrons required for bond formation are shared by only one atom, only nitrogen atom, and therefore arrow is showed in that direction, nitrogen to boron. This way arrow is showed, nitrogen to boron, and such a type of compounds are known as coordinate complex compounds. This is the coordinate complex compound formed after the neutralization reaction according to Lewis theory of acid and base. This is the coordinate bond. The bond formed by unequal sharing between two atoms is known as coordinate bond, and the complex so obtained by acid base reaction is therefore known as coordinate complex compound. So this is the Lewis theory of acid and base, on the basis of which all acids and all bases are explained. Now the next point is ionization of acid and base. This is important point in order to explain the salts, how the formation of salt take place. This point is very much important in order to identify the type of salt. See, ionization of acid and base. We know acids gives H plus ions, bases gives OH minus ions whenever they are dissociated. So depending on whether the degree of dissociation is 100% or it is less than that, there are two type of acids and two type of bases. We have seen the electrolytes and non-electrolytes. What is electrolyte? Electrolyte is a substance which whenever added to the water undergo dissociation giving the ions. Non-electrolyte is a substance which whenever added to the water undergo dissolution, not dissociation. It undergo dissolution but present in the original molecular formula, remain as it is in the original molecular formula. Further we have studied electrolytes are classified as strong electrolytes and weak electrolytes. Strong electrolytes undergo 100% dissociation, complete dissociation, whereas weak electrolytes undergo incomplete dissociation, partial dissociation, in which degree of dissociation is never 100%. It is not 100%. That type of electrolytes classification we have studied. Similarly, acids and bases are classified on the basis of their degree of dissociation. The acids which will undergo complete dissociation are known as strong acids, like HCl, H2SO4, HNO3, then HBr, HI, etc., HI, hydrogen iodide, etc. These are known as strong acids because these are the acids which will undergo complete dissociation. For example, HCl on dissociation giving H plus and Cl minus ions. 100% dissociation take place. Irreversible dissociation take place. Therefore, arrow is shown in only one direction. Only one direction. because HCl undergo complete dissociation. Secondly, weak acids. Strong acid undergo complete dissociation, whereas weak acids will undergo incomplete dissociation, partial dissociation, like acetic acid CH3COOH, formic acid HCOOH, hydrochloric acid HF, organic acids. Almost all organic acids are nothing but weak acids because they undergo incomplete dissociation. So, if we consider HCOOH, it undergo incomplete dissociation, giving H plus HCOO minus, formate ion and H plus ion. Reversible means these ions are present in equilibrium with unionized molecules of formic acid, so it is known as a weak acid. Then third one, strong bases, same as that of strong acids. The bases which will undergo complete dissociation, forming maximum number of OH minus ions, maximum number of hydroxide ions, are known as strong bases. The examples, common examples are sodium hydroxide, then potassium hydroxide, lithium hydroxide. These are nothing but the strong bases. These are the strong bases since they will undergo complete dissociation. And fourth one, weak base, the substance which will undergo incomplete dissociation, partial dissociation, like magnesium hydroxide, then ferric hydroxide, then calcium hydroxide, copper hydroxide. These are known as weak bases because they will not undergo complete dissociation. They undergo partial dissociation, partial means reversible dissociation. Both ions as well as unionized part is present. They are known as weak bases. So, ionization of acids and bases, here we have seen, is important to classify the acids and bases, and this is important in order to find out the type of salt. From which combination the salt is obtained, that is the important part in this chapter we have to study, and there you will come to know that classification of acids and bases is also important. Now the dissociation constant of acid and base. Dissociation constant of acid and base. For the reaction, we know equilibrium constant. How to calculate the equilibrium constant for a given chemical reaction, that we know. Equilibrium constant is calculated for which type of reaction? Reversible reaction or irreversible reaction? Reversible reaction. Always the dissociation constant, equilibrium constant is calculated for the reversible reaction. Here we have to calculate the dissociation constant, same as that of equilibrium constant. Dissociation constant is also to be calculated for reversible reaction. So dissociation constant can be calculated only for which type of acids? Is it calculated for strong acid or weak acid? Weak acid, because that will undergo incomplete dissociation. Similarly, Dissociation constant can be calculated for which type of bases? Is it for strong base or weak base? It is for the weak base because that is undergoing partial or incomplete dissociation. So let us see how to calculate the dissociation constant of acid and base. Since strong acids and strong base undergo complete dissociation, strong acids and strong bases undergo 100% dissociation. The degree of dissociation is 100%, irreversible. Equilibrium is absent. Therefore, dissociation constant for strong acid and strong base cannot be calculated. That law of mass action cannot be applied for strong electrolytes. Similarly, that cannot be applied for the strong base as well as strong acid. Only that is applicable for weak acid and weak base. So let us consider weak acid. Dissociation constant of weak acid. Let Ha is weak acid. So is it undergoing reversible or irreversible dissociation? Reversible dissociation. Forward reaction is possible as well as backward reaction is also possible. It undergo dissociation giving H plus and A minus ions. This is weak acid, therefore forward reaction is possible. Backward reaction is also possible and it undergo reversible dissociation in this manner. By applying the law of mass action, we know the rate of forward reaction, we know the rate of backward reaction. Their ratio is taken and that ratio is nothing but the equilibrium constant. Over here for acid, the equilibrium constant K will be equal to concentration of product H plus A minus divided by concentration of HA. This is the equilibrium constant, but since dissociation takes place, therefore it is known as dissociation constant of acid Ka. Dissociation constant. So dissociation constant of acid is nothing but the equilibrium constant. Equilibrium constant of dissociation reaction at equilibrium. Dissociation constant is nothing but the equilibrium constant at equilibrium for a dissociation reaction of weak acid. Because weak acid undergo partial dissociation, reversible dissociation or incomplete dissociation. Same is the case for weak base. Weak base. Let us consider BOH is weak base. We know bases are the substances which undergo dissociation giving hydroxide ions. So BOH on dissociation giving B plus and OH minus ions. Bases are giving OH minus ions. This is weak base, therefore forward reaction is possible. Degree of dissociation is not 100%. Forward reaction is possible as well as backward reaction is also possible. To this equilibria, by applying the law of mass action, rate of forward reaction can be calculated, then rate of backward reaction can also be calculated, and from the rate of forward and backward reaction by taking the ratio, we know we can calculate the equilibrium constant K equilibrium. We can calculate equilibrium constant K will be equal to concentration of products divided by concentration of the reactants. B plus OH minus upon BOH. This is the equilibrium constant for this reaction. Since dissociation takes place, it is known as a dissociation constant, and it is the dissociation constant for base, so written as Kb. Dissociation constant is therefore an equilibrium constant at equilibrium for a dissociation reaction. Therefore, dissociation constant can be defined as an equilibrium constant at equilibrium for dissociation reaction of either weak acid or of a weak base. In that manner, dissociation constant can be calculated. Since we know the calculation of dissociation constants, this type of equation can be applied for all the weak acids as well as weak bases, and one can calculate the value of either K or Kb if we know the concentrations of product and concentrations of the reactant. Same as that of the equilibrium constant, we can calculate the dissociation constants here also. So what is the part we have completed over here? We have seen first of all Lewis theory of acid and base. Secondly, classification of acids and bases: strong acid, strong base, weak acid and weak base. And then we have seen the dissociation constant of weak acid and weak base. This is not applicable for the strong acid and strong base, since they will undergo complete dissociation. They will undergo 100% dissociation. Now the Oswald dilution law for weak acid and weak base, that part we will see in the next lecture.